Okay, good morning, class. Today I just want to talk about the sequences in series, the convergent divergent tests for calculus BC. So here's the chart that it shows all type of series, whether that's considered convergent or divergent. Okay, let's start with the basic one. So let's say that series we do have a summation of a sub n equals 1 to infinity. So if the series converges, so that means, this one, it doesn't show anything like that, so it doesn't apply. But if that's diverge, so that means the limit as n goes to infinity, so that does not equal 0. So this one is called the n-term test for divergence. And this one should be the first test you use. It doesn't matter what happened. So for a sub n, if you see anything like that, so this one is for the divergent test. So let's say that you do have a geometric series test. So geometric, that means the common ratios. So the common ratio, let's say absolute value of the common ratio is less than 1. So it guaranteed that the series is always considered converge. Okay? So but the thing is that if that diverges, so that means the common ratio, the absolute value of that number, it's always greater than or equal to 1. So back to what you guys did in Algebra 2 and Pre-Calc. So if that's considered infinite geometric, so the way to find the sum can be always found by using a sub 1 over the quantity of 1 minus r. Again, r is called the common ratio. And the other type of series is called the p-series test. So you see the patterns like 1 over n to the power of p. Okay, so let's say that p is greater than 1, so the power it's greater than 1. So that means the number, if you try to expand, is going to be getting smaller and smaller and smaller. And that means so that the series is going to be converge. And then for the diverge, so that means p is less than 1, because if that's getting smaller and smaller, that means the whole number is going to be getting bigger and bigger. And also this one can be used for the harmonic series when p equals 1. So if that's harmonic, so that means the series is also considered diverge. And integral test. Integral test, that means you want to find out the integrals. So let's say that integrated, and you can find out the finite number for the area under the curve. So that's always considered converge. But the thing is that if that's infinite, so that if that's considered infinite or the limit it's not shown or going to infinity, so that means always considered diverge. So f of x must be continuous and positive, and it's what? Decreasing. Okay, so that's a condition you have to satisfy before you apply the integral test. And the one that we use kind of common is the direct comparison or the limit comparison. So the difference between these two, so for the limit comparison, we'll talk about that in a minute, but let's talk about the direct comparison. So for the direct comparison, we do have that a sub n, and a sub n is run between 0 and b sub n. So you see that 0 is less than or equal to a sub n, but it's less than or equal to b sub n. Well, the thing is that if b sub n converges, so that means a sub n also converges. But the thing is that if that 0 is run between, b sub n is run between 0 and a sub n. If b sub n diverges, so that means a sub n also diverges. So this one, to show the convergence, find a large series. And to show the divergence, find a smaller series. And the other one is called the limit comparison test. So for the limit comparison test, so usually we use that for the L'Hopital's rule to find out the limit. Okay, so using the L'Hopital's rule if necessary, or you can use any kind of technique to find out the limit. So the thing is that it's inclusive if the limit equals 0 or infinity. But the thing is that if the limit is greater than 0, and for b sub n converges, so that means a sub n converges. But the thing is that a sub n over b sub n is greater than 0. If that b sub n diverges, so that means a sub n diverges. Okay. And then for the alternating series test, so you see that -1, so it's negative, positive, negative, is always called alternating. So one thing that you need to compare that, you want to find out the higher term. So a sub n is always like an n term. But the thing is that I can always find out the next term after a sub n. So you see that a sub n plus 1 is less than or equal to a sub n. And then the limit of a sub n as n goes to infinity, if that equals 0, so that means the series considered converge. But the thing is that if a sub n does not equal 0, so that means for a sub n, then that will be considered diverge. So this one must prove that the limit equals 0 and that term are decreasing. So the term is getting smaller and smaller. And then the last two, then that'll be the ratio test and the root test. Again, they're quite similar sometimes, but the things that it's very easy to find out which one to use. Ratio is always the comparison of the higher term and the lower term. And then for the root test is always involved with the radical, with the n root. And n is always the positive integer. So for the ratio test, again, so if the ratios is considered less than 1 for the limit, and that means the series of a sub n is always considered converge. And then for that ratio, if that a sub n plus 1 over a sub n for the absolute value of the quantity, if that's greater than 1, so that means the series will be considered diverges. And also test fail if that the limit equals 1, so this one would be considered inconclusive. So that means you cannot determine anything. And then for the root test, it's quite similar. If that nth root of that radical's absolute value of a sub n it's less than 1, then that the series would be considered converge. And then limit n root of absolute value of a sub n is greater than 1, so that means the series got to be diverge. And then test fail. So again, this one is just inconclusive. So hopefully this chart, it helps you to figure out which one to apply and which one to use. And then the next one, I'm going to show you some of the example. So and see which one that is considered convergent and divergent for the series. Okay, so now let's go to the PowerPoint here. Okay. So let's start it off with the geometric. Okay, so for the geometric. So let's say that, so this one is just a definition of the sum of a geometric series. If that's considered infinite, infinite, that means R, the common ratio, is absolute value of the common ratio is less than 1. So the way to find a sum, it's always being defined by using A over the quantity of 1 minus R. Okay, so A, which is the first term of the series, and then R is the common ratio. So let's say that we do have something like this. A1 obviously is considered 1/2, and common ratio, it's also 1/2. So you see the series like this, it's always considered converge. And also this one right here, negative 4/5 common ratio, putting the absolute value, it's greater than, well, it's less than 1. So also the series is considered convergent. But for this one right here, 2 is greater than 1. So the series would be considered diverge. Again, once you find a sum, you can get a sum, it's a finite number, so they're always considered convergent. But this series diverges because that common ratio is greater than 1. And also you'll see like a repeating decimals. So let's say like 0.080808 with 08, the last 2 digits with the bar. If you try to extend it, try to put it into the fractional form, so it's written like this. So this one is called the infinite geometric series. Again, you see that the common ratio, it's 1 over 10 to the power of 2. So A1 is just like A over 10 to the power of 2. So again, you can find a sum, which is what? A over 99. So that means the series is considered convergent. So series known to converge or diverge. Again, so this one is just a summary. Geometric series, common ratio is less than 1, always considered convergent. And then the repeating decimal converges. Telescoping series converge. So telescoping, you'll see that in a minute. I'll let you know which one that is. And then a necessary condition for convergence, limit as n goes to infinity for n term in sequence is 0. So that's just the first one you have to test always. If the limit as n goes to infinity for the n term it's not 0, then the series is considered diverges. Convergent divergence. So here's some of the example. Okay. And this one can be founded by using the long division. You try to use the long division of the synthetic, you end up with 1 over 10, and then plus that the remainder over the divisor. So this one you can say that's like a telescoping. So the telescoping is always considered convergent. And then this one right here, geometric. So geometric, so you see that the common ratio, it's greater than 1. So this one would be considered diverge. And also this one, it's considered geometric. So A1 would be 4, and then common ratio would be considered 1 over n. 1 over 2. So 1 over 2, so that's a common ratio, so that would be considered less than 1. And this series, consider converge. So a sequence in which each term is less than or equal to the one before is called a monotonic, non-increasing sequence. If each term is greater than or equal to the one before it, it's called a monotonic, non-decreasing. So monotonic sequence, that is bounded, so it's convergent. A series of a non-negative term of converges if its partial sum are bounded from above. Okay, so that way it's always considered converge. So this one is for the integral test. So we talked about that earlier for the integral test. Again, so there's certain kind of condition. It must be continuous, positive, decreasing functions for the value of x for all value of x which is greater than or equal to n. N is a number. And the series and the corresponding integral shows both converge or both diverge. Again, if the sum can be found, so that means consider converge. If the sum cannot be found, if that's infinity, then that would be considered diverge. So just like finding the area under the curve. So using the integral test, so here's one of the examples. So a sub n, so then that'll be n over n squared plus 1. So it's the continuous functions, and it's showing that it's decreasing, so it's getting smaller and smaller, so we can use the integral. So this one, basically, we can use that f of x as x over x squared plus 1, rational. And try to integrate it by using the improper integration. So limit, so b goes to infinity, 1/2, and then 2x over x squared plus 1 dx. So this one can be found by using the natural log with the integral, and then integrate it from 1 to b. So plug in that f of b minus f of a, and then take the limit as b goes to infinity. So b goes to infinity, natural log of infinity, which is considered infinity. And this one is just a constant. So infinity minus a constant, it's always infinity. And therefore this series would be considered diverge. So the improper integral diverges. Thus the series diverges. So here's another example. Again, so using that, the substitution, replace all n by x, and then integrate it by using the improper integration, and you'll find out that it's considered pi over 4, so which is considered a finite number, so the improper integral converges. So that means the series converges. And here's the harmonic series and the p series. So for the p series, so if the power is greater than 1, so that means the entire series is always considered convergent. Okay? So if p series converges, if p is greater than 1, diverges, if p is less than 1, or p equals 1. Okay, so here's some of the example. So you see that p, it's 1. So this one is called the harmonic. Harmonic, that means the term is getting smaller and smaller, and it looks like it's going to be considered converge. But the thing is that eventually it's going to be any kind of random number. Okay, so this one's considered diverge. Identify which series converge or which one converge. Okay, so here's the one. So p series. So p is less than 1, so obviously this one diverges. And 1 over n to the power 1/2 also consider what? Diverges. And then pi over 3. Pi over 3, pi is 3.14 divided by 3, then that'd be considered 1 point something. So this one is considered converges. And 1 over n, harmonic, so this one is diverge. And 100 over n squared, again p is greater than 1. So this one converge. And then this one's kind of like a geometric. Okay, so geometric. And then common ratios. So it's got to be less than 1. It is. So that's why this one also considered conversion. And now the direct comparison test. Okay, again, so this one's the condition that you need to satisfy. So A sub n. The one that I showed you before, that's called B sub n. You can use that C sub n as well. So if A sub n converges, if there's a series, C sub n. So this one's kind of like a smaller series compared to A sub n. Okay, so we'll take a look at that example in a minute. Comparisons, so quite similar. So if the limit can be found, okay, so let's say C is less than infinity. So if B sub n converge, if both converge, well, if this one is true, that means either both converge or both diverge. So if that equals 0, so they always guarantee that's converge. So B sub n converges, then A sub n converges. So the comparison test, you got to be you got to be very careful with the way to compare the sequence, the series. Depends on which way that you want to use for B sub n, and it's quite similar to that A sub n. So if that equals 0, so that they always consider converges. Infinity, again, the limit cannot be found, so it goes on forever, so that would be considered diverge. Again, convergent or divergence, so again, it's all about the comparisons. So this one and also this one, you can use that 1 over 3 to the power of n for the comparison. And this one here, you can use that the ratios of nth root, well, root of n over n squared, and doing the comparison. And this one, you can use that b sub n as 1 over square root of 3n. Okay, so alternating series, the sign change. Okay, so for the alternating series, so certain kind of conditions that you need to satisfy. So a sub n is always positive, and a sub n is greater than or equal to a sub n plus 1 for n is greater than any arbitrary number for some integer n. And then a sub n is getting close to 0. If any one of the condition is not met, that means the series diverges. Okay, so for the absolute value, for the absolute and the conditional convergence, a series a sub n of the summation of n equals n to the infinity, it's absolutely convergent if the corresponding series of absolute value of that absolute value of a sub n converges. And a series that converges but does not converge absolutely, so that's called converges conditionally. And every absolute convergent series converges. Okay, so here's some of the practice. So you want to take the absolute value of that a sub n. If the absolute value of a sub n converges, so that means the series converges. Okay, so here's some of the example. Okay, so now, like this type of problem here, so this one's showing that alternating. So negative 1/3, negative 1/9, plus 1 over 27, plus 1 over 81, minus, so on and so forth. Again, this one looks like it's considered convergence because that a sub n is going to be getting close to 0, and it's alternating. So a sub n plus 1 is actually less than a sub n. It's getting smaller and smaller. And this one, we can use that also the comparison test. Okay, so using the comparison test, we do have that. Instead of using this whole thing, so this one can be considered 1 over 3 to the power of n. So this one, 1 over 3 to the power of n, is convergent geometric series because at the common ratio, it's 1/3. A1, it's just 1. Then the given series is absolutely convergent. Again, it's the comparison. So instead of taking all this, so we just apply that 1 over 3 to the power of n for the comparison. So here's another example. Alternating. So this one converges by the alternating series steps. Again, so the pattern is getting smaller and smaller. So it's a decreasing pattern. And then we take the absolute value. So absolute value is going to be considered positive, positive, positive. But this one will be considered diverge because that with the direct comparison with the harmonic series. So harmonic series, that means it's like 1 over n for the comparison. Because harmonic is considered divergence, so that means this one is also considered divergent. The given series is conditionally convergent. Well, because that without the absolute value, it's converge. But with the absolute value, diverge. So this one is called a conditionally convergent. Okay, so here's another example, alternating. And by the n-term test for the divergence, the series diverges. Okay, so here's one of the examples. So alternating converges by the alternating series test. Again, the term is getting smaller and smaller. And then with the absolute value, this one is considered the p series. So the value p is 1/2 because that's the radicals of 1, radical of 2, radical of 3, radical of 4. So this one will be considered diverge. Again, absolute value, if that's considered divergent, but for the regular one, it's convergent. So that means it's called the conditionally convergent. And then the ratio test. So the ratio test is always that limit n goes to infinity, a sub n plus 1 over a sub n. So that equals a value, an arbitrary constant. Then the series converges if p is less than 1. Again, this value got to be less than 1. The series diverges if p is greater than 1. And then the test is inconclusive if p equals 1. So that means nothing we can find out. So you have to use another type of test for that. And the root test, so absolute value of a sub n and then nth root of the quantity, if that equals the limit. Then the series converges if L is less than 1. The series diverges if L is greater than 1, or it's infinite. And the test is inconclusive if L equals 1. Okay, so here's some of the following example, so we can practice with. So this one you just need to raise up that power by 1, so you can use that. It's 2 to the power of n plus 1 and then n plus 1 factorial. And this one too, so 3 to the power of n plus 1, and then this one would be n plus 1 quantity square, and then 2 to the power of n plus 2. And then you want to use the ratio. By the time you're using the ratio, you'll get something cancel, reduce. If the limit, well, if that's going to be considered less than 1, if the limit is less than 1, then that means it's considered convergent. If the limit is greater than 1, then that'll be divergent. Equals 1, then that'll be inconclusive. Okay, so this one you can apply e to the power of 2n plus 1. And then n plus 1 to the power of n plus 1. So again, here's the chart that just summarized what we were doing. So it's quite similar to the one that I talked about earlier today, but I prefer the earlier chart better because this one is kind of a little bit confusing. And one yes, and then you have to move on to the next one. Okay, so try to use the first 5 minutes video, the chart that I showed you early. Okay, so the power series, we'll talk about that for the other video. Okay, so thank you for watching the sequences in series, the series test today.